Vibration analysis, causes of misalignment in driver and driven machines, understanding factors leading to mechanical component misalignments. Machine misalignment overview, types of misalignment, driver and driven equipment characteristics, poor installation practices, foundation and baseplate issues, thermal growth effects, operational and process-related causes, wear, aging, and component degradation, vibration and external influences, consequences of machine misalignment, detection and diagnosis of misalignment, prevention and best practices, conclusion and key takeaways. Machine misalignment refers to the condition in which the rotational centerlines of two or more coupled machines, such as a driver and a driven unit, are not aligned within acceptable tolerances. In industrial rotating equipment, proper alignment ensures that power is transmitted efficiently from the driver, typically an electric motor, turbine, or engine, to the driven machine, such as a pump, compressor, fan, or gearbox. When alignment is incorrect, excessive forces are introduced into the mechanical system, leading to vibration, heat generation, and accelerated wear of components. Misalignment is one of the most common root causes of rotating equipment failure and is frequently underestimated during installation and maintenance activities. From a reliability perspective, even small deviations in alignment can significantly shorten bearing life, damage couplings, and increase seal failures. In addition to mechanical damage, misalignment has a direct impact on energy efficiency, as additional power is required to overcome friction and dynamic losses. Understanding misalignment is therefore essential for maintenance engineers, reliability professionals, and operations personnel. It is not merely a maintenance issue but a system-level problem influenced by design, installation, operation, and environmental conditions. A clear understanding of misalignment fundamentals provides the foundation for identifying root causes, implementing effective corrective actions, and improving overall equipment reliability and lifecycle cost. Misalignment in rotating machinery is generally classified into three main types: angular misalignment, parallel, or offset, misalignment, and a combination of both. Angular misalignment occurs when the shafts of the driver and driven machines intersect at an angle, resulting in different shaft centerlines across the coupling faces. This type of misalignment often generates axial forces and causes uneven loading on bearings and couplings. Parallel misalignment, on the other hand, occurs when the shaft centerlines are parallel but offset from each other, creating radial forces that increase vibration and wear. In real-world industrial applications, combined misalignment is the most common condition, where both angular and parallel misalignment exist simultaneously. Each type of misalignment produces distinct vibration patterns, thermal signatures, and wear characteristics, which can be detected through condition monitoring techniques. Understanding these types is critical because corrective actions and alignment methods must address both angular and parallel components to be effective. Failure to recognize combined misalignment often results in repeated alignment issues and premature component failures. Proper identification of misalignment types allows maintenance teams to apply precision alignment techniques, such as laser shaft alignment, to restore acceptable operating conditions and prevent recurrence. In rotating machinery systems, the driver is the source of mechanical power, while the driven equipment performs the intended process function. Common drivers include electric motors, steam turbines, gas turbines, and internal combustion engines. Driven machines typically include centrifugal pumps, positive displacement pumps, compressors, blowers, fans, mixers, and gearboxes. Each type of driver and driven machine has unique mechanical characteristics that influence alignment sensitivity. For example, high-speed machines are generally more sensitive to misalignment due to increased dynamic forces, while machines with long shaft spans may experience greater deflection. Coupling types, such as flexible, grid, or gear couplings, can tolerate limited misalignment but should never be relied upon to compensate for poor alignment. Additionally, differences in machine stiffness, mass, and operating speed between the driver and driven unit can contribute to alignment challenges. Understanding the characteristics of both machines is essential for proper alignment planning, including selection of alignment tolerances, shimming strategies, and thermal growth considerations. A system-level view of the driver-driven relationship helps ensure long-term reliability rather than short-term correction. Poor installation practices are among the most common causes of machine misalignment. Misalignment often begins during initial equipment installation due to lack of precision, inadequate tools, or insufficient training. Common issues include improper shimming, failure to correct soft foot conditions, and reliance on straightedges or visual alignment methods rather than precision instruments. Soft foot, where one or more machine feet do not make proper contact with the base plate, introduces frame distortion when bolts are tightened, leading to immediate misalignment. In many cases, alignment is performed without considering final operating conditions, such as thermal growth or pipe strain, resulting in acceptable alignment at rest but severe misalignment during operation. Time pressure during commissioning can also lead to skipped steps or incomplete verification. Poor documentation and lack of standardized procedures further increase the likelihood of misalignment. Addressing installation-related causes requires disciplined alignment procedures, proper use of precision tools, and a strong focus on fundamentals such as base flatness, bolt integrity, and machine stability. Investing time in correct installation significantly reduces future maintenance costs and unplanned downtime. The foundation and baseplate play a critical role in maintaining machine alignment throughout the equipment lifecycle. Weak, cracked, or improperly designed foundations can allow movement under operating loads, leading to progressive misalignment. Baseplates that are not properly machined, leveled, or grouted may distort when anchor bolts are tightened or when the machine reaches operating temperature. Poor grouting practices can leave voids under the baseplate, reducing stiffness and allowing vibration-induced movement. Over time, foundation settlement or concrete degradation can also alter alignment conditions. Environmental factors such as moisture, chemical exposure, and temperature fluctuations may accelerate foundation deterioration. Because alignment depends on the stability of the entire support structure, even perfectly aligned machines can become misaligned if the foundation system is compromised. Effective prevention includes proper foundation design, high-quality grouting, routine inspection, and periodic verification of baseplate integrity. A stable foundation ensures that alignment efforts remain effective over the long term. Thermal growth is a significant and often underestimated cause of machine misalignment. During operation, machines experience temperature increases that cause components to expand. Because drivers and driven machines may operate at different temperatures or be constructed from different materials, they can expand at different rates and directions. This differential thermal growth can shift shaft centerlines and introduce misalignment that was not present during cold alignment. For example, a pump handling hot fluids may grow vertically and horizontally, while its driver remains relatively cooler. If thermal growth is not accounted for, the machine may be severely misaligned at operating conditions despite being well aligned at ambient temperature. Modern alignment practices address this issue through hot alignment targets, thermal growth calculations, and historical operating data. Understanding and compensating for thermal effects is essential in high-temperature applications and critical equipment. Failure to do so often results in recurring alignment problems, excessive vibration, and reduced component life. Operational and process-related factors can significantly contribute to machine misalignment over time. One common issue is pipe strain, which occurs when connected piping exerts excessive forces on the machine casing due to poor piping alignment or thermal expansion. These forces can distort the machine frame and shift shaft positions. Process upsets, such as sudden pressure changes, flow variations, or cavitation, can introduce dynamic loads that affect alignment. Additionally, operating equipment outside its design envelope, such as at higher loads or speeds, increases mechanical stress and accelerates alignment degradation. Frequent start-stop cycles can also contribute to movement and loosening of components. These operational influences highlight the importance of considering the entire system, not just the machine itself. Collaboration between operations, maintenance, and engineering teams is essential to identify and mitigate process-related alignment risks. Proper piping design, flexible supports, and controlled operating practices play a key role in maintaining alignment stability. As rotating equipment ages, normal wear and component degradation can gradually lead to misalignment. Bearings wear over time, increasing internal clearances and allowing shaft movement. Couplings may degrade due to fatigue, lubrication issues, or excessive misalignment, reducing their ability to transmit torque smoothly. Looseness in bolts, shims, or mounting hardware can develop due to vibration and thermal cycling. Even minor wear can accumulate, altering the original alignment condition. In older equipment, repeated maintenance interventions without proper alignment verification can further compound the issue. Aging infrastructure, such as corroded baseplates or fatigued foundations, also contributes to alignment instability. Recognizing wear-related misalignment emphasizes the need for periodic alignment checks as part of preventive and predictive maintenance programs. Proactive replacement of worn components and systematic verification of alignment help extend equipment life and prevent unexpected failures. External vibration and environmental influences can both cause and worsen machine misalignment. Nearby operating equipment may transmit vibration through shared foundations or structural steel, leading to gradual movement of machines. Poor mounting practices, such as inadequate anchoring or uneven support, increase susceptibility to vibration-induced misalignment. Dynamic loads from unbalanced rotors, belt drives, or gear mesh forces can also introduce cyclic stresses that affect alignment. Over time, these forces may loosen fasteners, deform baseplates, or shift machine positions. Environmental factors such as seismic activity, wind loads on outdoor installations, or temperature fluctuations can further influence alignment stability. Understanding these external influences is critical for equipment installed in complex or harsh environments. Mitigation strategies include proper isolation, structural reinforcement, and regular condition monitoring to detect early signs of movement or misalignment. The consequences of machine misalignment extend far beyond increased vibration levels. Misalignment accelerates bearing and seal wear, leading to frequent failures and unplanned downtime. Couplings experience excessive stress, reducing their service life and increasing the risk of catastrophic failure. Energy consumption rises as friction and mechanical losses increase, negatively impacting operating costs and sustainability goals. Misalignment also contributes to elevated temperatures, lubricant degradation, and noise emissions. From a safety perspective, severe misalignment can result in shaft breakage or component ejection, posing risks to personnel. The cumulative financial impact includes higher maintenance costs, lost production, spare parts consumption, and reduced equipment availability. Understanding these consequences reinforces the importance of addressing misalignment proactively. Correcting root causes rather than repeatedly fixing symptoms is essential for achieving reliable, efficient, and safe operations. Effective detection and diagnosis of misalignment rely on a combination of precision tools and condition monitoring techniques. Laser shaft alignment systems provide accurate measurement of shaft positions and allow correction to tight tolerances. Vibration analysis is widely used to identify misalignment-related vibration patterns, such as high axial vibration or specific harmonic frequencies. Thermal imaging can reveal localized heating at couplings or bearings, indicating excessive friction. Visual inspection remains valuable for identifying obvious issues such as coupling wear, looseness, or soft foot conditions. Trend analysis and historical data play a crucial role in distinguishing misalignment from other faults such as imbalance or bearing defects. A systematic diagnostic approach ensures that misalignment is correctly identified and addressed, preventing unnecessary repairs and improving maintenance effectiveness. Preventing machine misalignment requires a structured and disciplined approach throughout the equipment lifecycle. Best practices begin with proper foundation design, precision installation, and the use of accurate alignment tools. Correcting soft foot, minimizing pipe strain, and ensuring baseplate stability are essential steps. Alignment should be performed with consideration for thermal growth and actual operating conditions. Routine monitoring, including vibration analysis and periodic alignment verification, helps detect early deviations before failures occur. Training and competency development for maintenance personnel are critical to sustaining alignment quality. Standardized procedures, documentation, and alignment tolerances ensure consistency across the organization. By focusing on prevention rather than reaction, organizations can significantly improve equipment reliability, reduce maintenance costs, and extend asset life. Machine misalignment between driver and driven equipment is a common but preventable reliability issue. Its causes are multifaceted, encompassing installation practices, foundation integrity, thermal effects, operational conditions, wear, and external influences. Understanding these root causes enables maintenance and engineering teams to implement effective corrective and preventive measures. Precision alignment, when combined with stable foundations, proper operating practices, and ongoing condition monitoring, delivers significant benefits in terms of reliability, energy efficiency, and safety. Misalignment should be viewed not as an isolated maintenance task but as an integral part of asset management and reliability engineering. By adopting a proactive and systematic approach, organizations can reduce unplanned downtime, optimize performance, and achieve sustainable long-term operation of rotating machinery.